So we're going out into the universe, outside of the solar system. So the solar system is an island called the Milky Way with another 200 billion solar systems. So we got plenty of solar systems. Now, this is called the Milky Way galaxy. It's a rotating disk of stars, dust and gas, basically. That's all it is. Oh, there's a, big gigantic black hole in the very center of the Milky Way right here. So allow me to grab a nice spotlight.
Why does that
And
look white?
I'm sorry?
Why does it look white in the center?
All I hear is, why does it look light? That's what I heard.
No, white. White.
White. Do you see white? I don't see white. Where do
In
you
the
see white?
center of your image,
In the
it
center
looks
of my
like
image.
clouds.
This looks yellow to me.
Oh, okay.
This doesn't look yellow to you? If it's white, not yellow, you need to fix your monitor. Because
Why
it's
would
yellow.
you have to do that?
All right, so now let's get into the colors like she was talking about. Let's get into the colors. So the colors now, why are they different colors, right? Let's start. So what colors do we see? I was going to say that we see yellow here. So this yellow is in the center of the galaxy, and it represents what we call the bar of dust and gas in the galaxy. So there's a bar of dust and gas here going through the center of the galaxy. And then there's spiral arms coming from that bar. So imagine a bar of gold here. And this bar of gold is a whole bunch of old stars. We call the old stars population 2 stars. So there's a whole bunch of old, over the hill gang here. There's gigantic stars, red giants and red supergiants. That's why it's kind of yellowish. Red giants and red supergiants are really not red. They're really yellow. So that's where they are. They're right here. Lots and lots and lots of them. If you lived here in the center of the galaxy and you look up in the sky, there'd be millions of bright stars in the sky like Venus. It'd be amazing. The view here from the center of the galaxy should be fantastical, right? Besides yellow, we see blue. Blue represents luminous stars. From this distance, we're looking down on the Milky Way's disk, and we see something like billions of stars. It appears kind of like a cloud, but it's not. These are individual stars that make up the spiral arms of the Milky Way, and they're kind of bluish. So that blue is basically B stars, some O stars, some A stars, just very luminous young stars. We call the young stars in what we call the disk of the Milky Way, population 1. So we got 2 populations. Population 1, very young stars that were born, they're going to die, main sequence and all that, like the sun. And then we have population 2 here in the center. And this is the yellow stuff. Besides that, we also have some red patches here. We can see the red colors all over the place. If you notice, the red color is tracing the spiral arms. Just follow the red colors, patches, patches, patches of red color here. This is where the stars are being born. And we call these regions the H2 region. H, hydrogen, 2 for ionized hydrogen clouds. So H2 is the ionized hydrogen clouds. This is where stars are being born. We call these nebulas. Nebula means cloud, right? And so we also have places where it's not luminous like this, dark clouds like this. We call these the H1 regions, neutral hydrogen clouds. Now, why is this guy ionized and glowing, and why is this guy not glowing? Well, this guy is ionized and glowing because that's where the stars are being born. So the newborn stars are ionizing the hydrogen clouds. They blow away the electrons out of the hydrogen with their light. And then when the hydrogen grabs another electron, then they glow. So that's what we call ionized hydrogen clouds, the H2 regions. You know it's going to be on the exam. H1 regions, neutral hydrogen clouds. This one I'll explain to you later. This gives me this feeling that there is a higher powers besides, us, there's higher intelligence in the universe. Something is behind all these creation. All right, we'll talk about that later. So remember this H2 regions. H2 regions are ionized hydrogen clouds that are glowing. H1 regions are dark. This is neutron hydrogen clouds. They sit here doing nothing basically. There's no stars being born, maybe later, but not now. They're just sitting there. Then there is some dust. The dust is basically tar. That's what you get when you smoke a cigarette in the car. Your windows become, this film, the yellowish film covers your windows. And then it's kind of sticky. We call it tar in the cigarette. Now, eventually, that's going to become a black window. So really, the color of dust is black. And so we say these are the dust clouds. Very difficult to tell the difference from this image between the dust and the H1 region when neutral hydrogen clouds are. Now, there's also a bar of dust and gas going through the center, and we said the spiral arms coming from there. So why is there all these spiral arms? Well, two reasons. One reason is that the stuff in the center is rotating very, very quickly. Stars in the edge are rotating very, very fast. So imagine there is a few people in line, and they're all rotating around the center, except the one closer to the center is rotating faster. So they go around like this. The ones at the edge are going slower. You naturally form a hydrogen cloud. But now if you have a cloud that looks spiral, made of stars and gas and dust, then why does it sustain itself? It appears to sustain itself from what we call gravitational waves. Remember, till a few years ago, like 5 years ago, we didn't even know really these gravitational waves exist. Now we know for sure they exist. So they kind of keep these spiral arms in check. They kind of keep pushing them until they sustain their shape. So there you have it. Now, in the very, very center, a central black hole. It's a supermassive black hole, 4 million times the mass of the sun. Remember, it's like zero size, right? But it's got a pretty huge event horizon. These event horizons that form from gigantic, massive, supermassive black holes, you can actually go inside. You won't even know you're in there because gravity is very, spread out. You don't feel like your feet are being pulled in really hard and your head, left behind. You don't feel that at all here. But you're going to get destroyed anyways. You'll never be able to get out of there. So once you go in, you're not coming back out. And you're probably going to get fried to a crisp anyways.
Could I just get clarification? You said at the outside of the spiral, they go slower than in the center?
Yes, the rotation rates on the outside is exactly what I'm going to talk about right now. It's a big thing.
May I ask, Professor? I'm sorry. May I ask? You said that to piggyback off that question with the faster rotation in the center. You said it with the spiral, it makes a natural what cloud?
Spiral arms. It makes the spiral arms.
Okay.
I said, imagine, there's like 3 people standing in line here like this. The one in the center is going around really fast. The one out here going slower. The one out here going even slower.
Understood.
So you naturally have some guy falling behind and making a spiral arm naturally like this.
And you said something about a gravitational something?
Gravitational waves.
I put sustained by gravitational waves.
I'm sorry?
I put that the Milky Way is sustained by gravitational waves.
The spiral arms are sustained by gravitational waves. In other words, if you have, these arms, in time, they disperse and they're no longer arms. So these gravitational waves that emanate from the center of the galaxy, they kind of keep them in check. They keep them, this shape is maintained by these gravitational waves.
Thank you.
All right. So now I superimpose this picture on the older picture. This is a picture centered on the sun. There's the sun. These are called galactic coordinates. So that's the way they set up the galactic coordinates in the Milky Way, not from the center out, but from the position of the sun. Now, I'm going to show you what this looks like superimposed on top of the older pictures. We can see the spiral arms now. They have names. This one is called a Scutum Centaurus arm. And this side of it here, we don't even see from San Diego. We see it if you go to Australia, perhaps. And this is the Sagittarius arm. The Sagittarius arm is the Milky Way that we see from San Diego. So when you see the summer Milky Way rise at 11 o'clock tonight, that's the Sagittarius arm that you're looking at. On the other hand, if you see the Perseus arm, that will be in the wintertime. So in the wintertime, you're looking away from the center of the Milky Way. In the summertime, we're looking towards the center of the Milky Way. This makes a beautiful Milky Way that we see in the sky. I have all these pictures to show you, so don't worry about the details. I'll get into the details later. Now, we live in a place called Orion Spur, which is not exactly an arm. It's like a tiny little spur off an arm. You see that? So this is called the Orion Spur. That's where we live. Why do they call it Orion Spur? Because we're neighbors with the stars in Orion. So Orion constellation, the stars in it, they're in our neighborhood. So the stars that you see in our neighborhood, they're all around here. That's where the stars are. That's what you're looking at. We don't see the stars further out because they just merge into the, the general Milky Way picture. So we don't really see individual stars. All right, now let's take a look at more details from the side. This is a side view of the same. So this is something we call the disk of the galaxy. The disk of the galaxy is what I just showed you. This is the disk of the galaxy, this blue thing. It's not very thick. It's maybe a couple of thousand light years thick. So it's not very thick, and it gets thick in the center. This is called a bulge. So we see the bulge and we see a disk here. And there's a whole bunch of stars on the outside. This is the halo of the Milky Way. So now let me point all that out to you. The diameter of the disk, where you can see the spiral arms, it's about 100,000 light years. That's a distance. So that means if you shine a flashlight here, it'll get to the other side in 100,000 years. Although, because there is so much dust and gas, your light is not going to go very far. Maybe about 10,000 light years, maybe about to here. So we don't see very far around us. Now, the solar system is halfway out. We're about 25,800 light years away from this central black hole right here. So just round it off to 26,000 light years from the center of the galaxy. We're in the outskirts of the Milky Way, halfway from the center to the edge. Right? All right, so that's where the solar system is. From this location, we go around the center of the Milky Way every 225 million years. Remember, this is not light years anymore. That's distance. This is time. 225 million years. And you might think, oh my God, that's a long time. Well, the solar system has been around about 18 times. Since the sun is 4.6 billion years old, the whole solar system has gone around a long, long time ago. And we've gone around 18 times so far around the Milky Way. So this is what we call the plane or the disk of the Milky Way. We also refer to this area as the zone of avoidance. Because if you look in the direction of the disk, this way, we don't see any external galaxies outside of the Milky Way. We only see dust and gas and stars. That's all we see. So this is called a zone of avoidance because the galaxies avoid this zone here from our location. The stars that we see away from the Milky Way will be up here. These are the stars that you see in the night sky. Stars above the plane or the disk of the Milky Way, stars below the plane of Milky Way, That's what you see in the sky when you look at the sky. Then when you look in the direction of the disk, you would see the Milky Way itself. And I'll show you. The center is bulged out. We call this the bulge of the Milky Way. This is where the old stars live. We call the old stars population 2 stars. There's stars in the halo as well. The halo surrounds the bulge itself here. There's the halo of the Milky Way. It's got a lot of dust and gas. Gases are hot out there, very, very hot. Most likely the gases came from supernova remnants, right? Supernovas, when they blow up, they blow gases out. So these gases end up in the halo eventually, and they're really going at a high speed. So they appear to be very hot. Not dense, just extremely hot gas. And there's some stars here too. It's possible that gravitationally some of these stars were knocked out, like they get expelled from the Milky Way like that. And some of these stars were also born in the halo as well. So there's the halo of the Milky Way. Now, population 1 and population 2 will be easy to remember if you remember. The stars in the disk of the plane, what we call the spiral arms, they're all population 1, young stars. And there's a lot of metals here because metals are expelled from supernovas, right? Lots of them here. In the center, population 2, out in the halo, population 2, bulge, population 2. So everywhere else, except for the disk, we have population 2, meaning old stars. And there's something very beautiful here too, in the halo. And this is called globular cluster. These are balls of stars. These balls have 10 million sometimes stars in them. Very, very old, and they're devoid of metals. They haven't exploded yet. They're extremely old. All giants and red supergiants here in the globular clusters. And globular clusters orbit the galaxy like this. In fact, I made a little video. I'll show you in a second. So I wrote this for you for your notes. Population of stars in the Milky Way, population 1 in the disk of the galaxy, population 2 in the bulge, in the halo, and the globular cluster stars, and the central portion where the bar is, B-A-R, just like where you go get a drink, a bar of the galaxy. It's like a bar of gold though, right? A bar of gold looks kind of like that, like the bar that we see here. There's the bar here. Goes right through the disk of the galaxy, and then the spiral arms emanate from the end of the bars. It's a beautiful galaxy. Now, let's see. The sun, the entire solar system, orbits, we said, every 225 million years, and it sounds like a long time. In reality, it's way too fast. We should be expelled. The entire solar system should be expelled from the Milky Way galaxy, but we're not. Something is holding us in. That's something we call dark matter halo. It surrounds the entire galaxy. We can't see it. That's why we call it dark. It's invisible. The only thing that we can detect is gravitational force from this dark matter. So where's this dark matter? It just covers the whole thing. It's like, it's in your room right now. It's in the sun. It's in the Milky Way. Everywhere is dark matter. Particles of dark matter are very mysterious. We haven't discovered them yet. They're just inferred from the gravitational forces. So we imagine the dark matter being like a hamburger bun. Can you imagine a hamburger bun where the Milky Way is the patty and the hamburger bun is holding the patty together? So yeah, so let's make Milky Way into a quarter pounder. So there's a quarter pound patty surrounded by a bun named dark matter. We can't see the dark matter though. It just has gravitational influence on the Milky Way. It holds it together. If it wasn't for the dark matter, we'd be shot out of the Milky Way in a second, like that. Amazing stuff, this dark matter. So the way we found it is that we looked at other galaxies as well as the Milky Way, and we discovered that they're all rotating more like a disk instead of following the solar system. Solar system is rotating in a Keplerian motion. Remember, period to the power of 2 is equal to average distance to the power of 3. P squared is equal to a cubed, Keplerian motion. Well, these guys are not following the Keplerian motion. That's where the dark matter was first theorized, back in the 50s. And now, for sure, we think there is dark matter. I think for sure there is something out there. And it's got 5 times the mass of regular matter. So me and you are made of regular matter? This stuff is made of stuff that is 5 times heavier than protons, 5 times heavier than regular matter we call baryonic matter, B-A-R-Y, baryonic matter. So baryonic matter is the regular stuff. Me, you, your dog, everybody's made of baryonic matter. This stuff is dark matter. And we think a lot more of the universe is made of dark matter than regular matter, actually. A lot
Professor,
more.
may I please see the last slide for one moment?
Sure.
Thank you.
You're welcome.
So baryonic matter is what everything is made up of?
Yeah, regular matter. Yeah, like
regular
atoms, protons, electrons, neutrons, everything. The stuff that we see anyway is the stuff that we detect. But this stuff is not baryonic matter. Dark matter is, well, we don't know what it is. That's why we call it dark. Every time we're zonked, we call it dark.
Where does the name baryonic come from?
From Barry, what was his name? That singer, Barry Manilow.
Gibbs?
Barry Manilow. No, I'm just kidding. I don't know where the heck it comes
Barry
from.
Manilow.
I don't know where baryonic name comes from. I'm sorry. These globular clusters are out here in the halo, and they go through the galaxy like this, we said, right? So we'll see that in a second here. Let's take a look at the orbits of globular clusters. Remember, these are balls of million suns, all of them population 2, red giants and red supergiants. Senior citizens, they're probably the oldest stars in the entire galaxy. I think that the stars in the halo, including the globular clusters, formed even before the disk of the galaxy. So imagine there's this huge cloud of gas that was spinning, and as it was spinning, these stars in the halo formed first, and then eventually this formed. Well, so globular clusters are moving perpendicular to the disk. They go right through the disk. Sometimes they capture stars with them. They take it with them. And so we see these captured stars as something we call blue stragglers. These blue stragglers shouldn't be in here in these globulars, but they're there. There's a few of them. They're not that many. So they pick up some gas, some dust, some stars, kidnap them, and leave the Milky Way. Takes them a long time, though, billions of years. So these orbits are kind of weird, like this. This is orbit of a simple globular cluster called Palomar 5. It's the 5th globular found in the Palomar Observatory in Mount Palomar. All right. Now just kick back and enjoy the pictures. I'm going to show you some of the pictures of what you see when we look at the Milky Way. Sagittarius arm. So when you look at Sagittarius arm, the center of the Milky Way is right here. That's where the supermassive black hole is. Let's see if I can figure out exactly where it is. There is the Sagittarius. It's right here, you guys. That's where the center of the Milky Way is. So remember, it tapers off over here. This is a bulge here. I love the Milky Way pictures that show, like a lake in the front like this. I think they're awesome. Very relaxing. I put these pictures in my room, they're just awesome pictures. This is more like what you see if you look at the sky tonight at 11 o'clock. It rises. By 3, 4 o'clock in the morning, it'd be fantastic. If you happen to be partying outside late at night, look at it, please. It's unforgettable. That's how I fell in love with astronomy, by looking at the Milky Way.
But do we have to be in the mountains to see that, or can we be in the city?
Well, you can go outside, like outside of San Diego, maybe even like just a few miles outside of El Cajon, even you should be able to see it in the east, rising. Okay. Later on in the summer, like in August, to be directly south. Then you really need to go like to Viejas. You can definitely see it from Viejas. So this is, can you guys recognize this? This is called Ayers Rock. Ayers Rock in Australia. So from Australia in the southern sky, you can see the center of the Milky Way much better. There is the centers right here. This is the bulge, and it tapers off on both sides here and here. So this is what the Milky Way looks like from Australia. You get the best views.
The darker parts are the disk.
What kind of thing?
The darker parts there, that's the disk.
This is the dust and gas in the disk.
Okay. Mm-hmm.
These are the disk itself, yeah. So the disk is behind this dust and gas. All the dust and gas is in the disk as well, but they just prevent us from seeing anything. This dust and gas blinds us. We can only see about 10,000 light years around us. So you have to use infrared cameras, radio telescopes, X-ray cameras, things like that to see the center of the Milky Way. Here's another picture of the Milky Way. This one is what we see. So the center of the Milky Way is here, and it just barely rises above our horizon. This is also from the southern sky, so it's just beautiful. Now you can see the reddish patches here. These are the ionized clouds of gas that I told you. The H2 regions, right? Roman numeral 2, H2 regions. Now this picture was taken with a filtered camera that just shows you hydrogen gas. So it's a regular camera that was modified, because regular cameras just take pictures of the Milky Way stars. You don't see these reddish colors. They're deep in the red, and regular cameras have a little filter that takes out the infrared part of the picture. And when they do that, they also take out some of the red. This is in that part of the red. It's about 650 nanometers. So deep into the red. And this is what they look like close up. This one here is called the Pillars of Creation. They're called the Eagle Nebula. This is the head of the eagle. This is the eagle itself. This is the talons of the eagle. Is holding this thing in his hand. And if you look closely, you will see something interesting. Stars are being born inside of here. You can't see it because this dust and cloud is just too thick. But you see the fingers. That's the sign that little baby stars are being born, and they're throwing a tantrum. They're overacting. They eject gases, just like human children. So these stars are blowing these jets of gas that sculpts these clouds of hydrogen gas, and it makes them glow like that. So
are those the T Tauri stars in there being developed?
Yes, the T Tauri stars are living inside of here. I'll show you the picture in infrared in just a second, but I want to show you the fingers first. So you can see these fingers, there's stars being born here, stars being born here, stars being born here, here. A whole bunch of stars being born. So now you ready? This picture, exact picture in the infrared. Now you can see the stars. There's the head of the eagle, body of the eagle, the talons, and that's what's holding in his hand. Now you can see inside of the cloud. These are the T Tauri stars, Linda. As the stars are being born inside of these clouds. If you notice, stars are not born individually. They're born hundreds at a time, sometimes thousands at a time. We call these open cluster of stars. The sun used to be in an open cluster of stars. That's where they are. That's where they're born, in these H2 regions. And then they ionize the cloud of gas, and the cloud of gas starts glowing. They look like this. Look at these tantrums these guys are throwing here. Look at these. These are all coming out of the gas. Look at this one here. Sheesh, sheesh, right? Look at this one. Another star is being born. Maybe multiple stars are being born here at the same time. So this is the H2 regions. We call them emission nebula because they glow. Emission nebula is the same as ionized clouds of gas in the Milky Way, same as H2 regions. So once these stars are born, right, they clean up after themselves, not like human children. So there's still some clouds left over. They blow away these clouds with the radiation pressure. Light has pressure. In fact, we can go solar sailing with the light of the sun. You just need a gigantic sail. Can you imagine having a sail to sail the solar system? Well, the inner solar system anyways. So there are plans right now to make bigger sails. There's a couple of sails there already. So instead of traveling with, liquid hydrogen and helium, you can go traveling with just sailing, just like you sail with the wind in the oceans. Except this is radiation pressure sailing. There might even be, ESPN broadcasting solar sailing events in the future. Your children will definitely see it. So I'm sorry?
Sorry, a bit far off from that. Would be maybe using that for interstellar movement.
Solar sailing?
But that is very far-fetched right now.
Yeah, solar sailing, though, means solar sailing from the light of the sun.
Not
what you're
actually.
talking about, is laser. Lasers can do the same thing. So they can have radiation pressure. So if you have gigantic lasers, you can blow something away into the nearest star system, like 4 light years away. It'll get there maybe in 1,000 years, something like that. It's possible. You'll see it. So these are called reflection nebula. Nebula means cloud. These are reflection. They're reflecting this blue of the blue stars that are being born here. Freshly born stars. Once they clean up, then they become like this. These are open clusters of stars. There's a whole bunch of stars that live here. Now, eventually, like if you have a lot of peas in a very thick soup, you throw a whole bunch of peas in. These peas are these stars here. If you stare at peas, then some of the peas go up, some of the peas go down, some of the peas are disturbed, some of the peas are dispersed. Eventually, these guys here are going to join the background. They're going to become like these stars. This is the Milky Way stars. So this is called a double cluster, and it's in the winter Milky Way, in the Perseus arm. And it's very unique. It's like 2 clusters living side by side. Young, very young. So eventually they're going to become these stars here after a few orbits around the Milky Way. So the sun used to be in one of these. We had thousands of brothers and sisters. They're all lost now.
Is it the orbit that spreads them out? Is it the orbit that spreads them out eventually, or the fact that...
Yeah, again, it's like steering it. If you go around a few times, the gravitational forces of nearby stars, the gravitational forces of general Milky Way, eventually will steer you. So as you orbit, you don't necessarily orbit straight. You go up, you go down. You get mixed in with the rest of the Milky Way.
I see.
You just become another star in the Milky Way. Cool. So somebody in the Milky Way galaxy, when looks at the sun, will see the sun like one of these little tiny stars here. So we're just one of these guys here. Okay. These are the globular clusters that I showed you. The globular clusters that orbit the galaxy perpendicular to the disk of the galaxy. There's like 1 million stars. You're looking at like 1 million stars simultaneously. It's mind-boggling in a telescope because, you're looking at seeing where the atmosphere is kind of like making them, twinkle, twinkle. You see 1 million lights twinkling in a telescope. It's one of the most amazing things you can see in a telescope. It's pretty cool. Here's another one the Hubble took. Just amazing stuff. Look at them. The more I show you, the more you'll be amazed. Look, every one of these is a solar system. All of them. Look at that. Just amazing. This is a Hubble Space Telescope taking a picture of a globular cluster. So that's what they look like. Spherical collection of 1 million or more stars here. We call it globular cluster. We have more than 150, perhaps 200. Some are on the other side. We can't really see them because of dust and gas, but they're there. So this will show us everything. This is called, I hope you can guess what this is called. Can you guys guess what this is called? Sombrero Galaxy. So sombrero looks like this. This is sombrero hat. So this is called Sombrero Galaxy. And the Sombrero Galaxy looks a lot like our galaxy. It has the bulge in the center. There's the disk. There's the dust and gas in the disk. Look at that. Spiral arms are here. So yeah. So these guys going around the center, they go a little slower than the stuff in the center, but not substantially. So the whole thing appears to be rotating almost like a disk. So bulge, halo, look at the halo here, right? There's a halo. And if you look closer, these are the globular clusters. These are not stars. These are globular clusters orbiting the galaxy. These are stars in the Milky Way. So we're looking through the Milky Way, outside the Milky Way, and we're looking perpendicular to the disk or close to it, away from the disk of the Milky Way. Remember, the disk of the Milky Way is called the zone of avoidance. You can't see any galaxies if you look in the direction of the disk. If you look perpendicular to the disk, 45 degrees to the disk, you can see outside the galaxy. So halo, bulge, disk, dust and gas, everything is here. Globular clusters.
Any black hole?
Black holes there too, yeah. Almost every major galaxy has a supermassive black holes, like millions of times more massive than the sun. So these are probably the seeds where the galaxy grew from, you know, like when we get to the Big Bang, we'll talk about that. There's going to be supermassive black holes at the beginning of the universe. And then eventually they collected some gas and dust and made galaxies, like our galaxy, like this galaxy. So they all appear to have a supermassive black holes in the center. This is something we just found out like 5 or 6 years ago. All right, now, why do I believe that there is a higher intelligence? There's a higher than us, right? Like, you can call it God if you like. I believe in it, but you don't have to. So this is why I believe in it. This is a map of the H1 regions, neutral hydrogen clouds, all right? So neutral hydrogen clouds are like radio stations. They emit radio waves. Specifically, radio waves with a wavelength of 21 centimeters. They're called 21 centimeter waves. So they're sending a radio wave out from all these little patches. This is where neutral hydrogen sits and sits and sits. And so like this part here, we don't even see this spiral arm. We don't see this spiral arm either. Neither this one or this one. We know they exist because we trace the neutral hydrogen cloud gases. So this is clouds of neutral hydrogen, H1 regions. They don't glow, but they send out radio waves. So what makes them send out radio waves? Well, imagine this is a proton. You know, protons are also moving rapidly. So this is positively charged, electrons negatively charged. So here's an electron orbiting a proton. In a cloud of gas we call H1 neutral hydrogen clouds, we have neutral hydrogen gas, right? These guys sit there for 5, 6 million years. All of a sudden, the electron knows. Electron changes the direction of spin. So instead of spinning this way, it starts spinning this way. And it sends out a radio wave. This radio wave has a wavelength distance between this peak and this peak, or crest to crest, is called 21 centimeter radio wave. So there's the wavelength from here to here. And it just comes out. So Depends. Some of them send it after a couple of million years. Some of them send it after 50 million years. And so my question to myself was this. Electron is the smallest thing in nature. It might just be a cloud. It doesn't even, have any size. How come something that tiny knows to send out a radio wave? I mean, it's quantum physics. It's quantum physics. Okay. How does the electron know quantum physics? Did the electron go to school? So it was born with quantum physics. Well, okay. Right? That's my question. It's like it doesn't have a brain. How does it work? How does it know quantum physics? How does it know how to act? That to me is higher intelligence. So that higher intelligence makes me believe in something like God. Not religion, God. All right. This is our neighborhood. So this is a neighborhood of the Milky Way. There's the Milky Way with its friends here. And close by, there is another gigantic galaxy. So this is the closest major galaxy to the Milky Way, called the Andromeda Galaxy. The closest galaxy is not the Andromeda. There's a whole bunch of galaxies that are closer, but this is the closest major galaxy within 10 million light years of the Milky Way. So there's another spiral galaxy here too called M33. Looks like a little pinwheel, like that. But this guy here is visible in the fall sky later in the summer, or in the fall, you'll be able to see this. The Andromeda Galaxy is about 8 times the size of the full moon. It's a giant thing in the sky. It's the farthest thing you can see with your naked eye. Without binoculars, without telescopes, you'll be able to see this fuzz patch. And this fuzz patch is called the Andromeda Galaxy. And the Andromeda Galaxy's got its own partners here. They're coming towards us. We're going towards them. In about 4 billion years, the Milky Way is going to be destroyed by a collision between it and Andromeda Galaxy. So that'd be for sure to be the end. There'd be nothing left of the solar system. So now we know for sure that the black holes are going to merge. And Andromeda Galaxy has a big one, 55 million times the mass of the sun black hole. So they're coming at us. We're going at them. There'll be a collision. Be kind of a cool collision. I'll show you guys collisions next time. Now, these are the galaxies that are orbiting us. Most of them are orbiting the Milky Way. There's 2 of them that are very famous. This one is called the Large Magellanic Cloud. This one is the Small Magellanic Cloud. So Small and Large Magellanic Clouds. You can see them in the southern sky. Now, we're in the business, when I say we, I mean the Milky Way, is in the business of swallowing up galaxies. They're smaller than us. So we had a collision a while back, and we're eating up this galaxy called Sagittarius, right? So Sagittarius galaxy is being eaten up by the Milky Way. It's in pieces now. There's another galaxy called Canis Major Dwarf Galaxy. That's the closest galaxy to the Milky Way. Excuse me. If you watch Star Trek, you know what assimilation is. We're assimilating. We assimilate in the Canis Major Dwarf Galaxy. It's inside of the Milky Way. So this blue is the Milky Way. This red is a remnant that was left over of Canis Major Dwarf Galaxy. You can see the arms here. Sun is right here, actually. So it turns out a lot of stars in the Milky Way are probably immigrants. They came from some other galaxy. Let's face it, Milky Way is a cannibal. We eat smaller galaxies. Eventually, we're going to be eaten up by a collision with Andromeda Galaxy too.
Will Andromeda also then explode or disappear, or will it still
there's
exist?
No explosion or disappearing. We're going to join black holes. So we're going to have like a 60 million times the mass of the sun black hole. And most likely, the stars in the bulge are going to survive. I'll show you collisions next time, so you can see exactly what happens, because it's very important. This is how galaxies evolve. So that's the evolution of galaxies we get into. This is the small and large Magellanic Clouds. Right? They're not like spiral galaxies like we are. In fact, they're irregular galaxies. And they were first noticed by Magellan. Magellan is the first person to circumnavigate the world, basically, but he dies. He dies as they're going from the Atlantic Ocean to the Pacific Ocean. First person to navigate from the Atlantic Ocean into the Pacific Ocean. He gets some kind of a virus, perhaps. We don't exactly know what. Black Death, maybe? So he dies. The sailors named these two after Magellan. So they must have liked Magellan. Must have been a nice guy. Large Magellanic Cloud, small Magellanic Cloud. They orbit the Milky Way galaxy. There are little buddies. And you can see them from the southern sky. You don't see them from the northern sky. You can see them from the southern Mexico too. So if you ever go to southern Mexico, look up. You can see the small and large Magellanic Clouds. Andromeda Galaxy. Andromeda Galaxy is its own partners. This one here is a little tiny elliptical galaxy. Another little tiny elliptical galaxy. They also orbit Andromeda Galaxy. Gigantic, massive black hole in the center here. Again, look, blue stuff, spiral arms, bulge stars, population 2 in Andromeda. It's a lot like the Milky Way. We're so similar, almost exactly the same size as the Milky Way. But in our class, if I ever ask you which one is more massive, say Andromeda. Milky Way doesn't have a big ego, so it doesn't matter. All right, so that's what these galaxies look like. You know, they have, some of them are just plain just stars. Some of them have dust and gas. And all the galaxies have been classified by Hubble. This is called the Hubble tuning fork diagram. He did it back in the 30s. He just took pictures of galaxies, thousands at a time, while he was smoking his pipe inside of the 200-inch telescope eventually. So they used to smoke pipe and cigarettes inside of the biggest telescopes in the world. Imagine that. So this is how he classified the galaxies. He said basically there's 4 types of galaxies: ellipticals, lenticulars, spirals, and irregulars. Irregulars means they don't have any shape. They're not classified according to shape. But this is all classified according to shape. So we start with ellipticals. Ellipticals go from E0 to E7. This refers to the eccentricity. E7 means more eccentric, more like a cigar. E0 means no eccentricity, more like a basketball. Perfectly spherical ball of stars. They don't have any dust and gas. They're all population 2. They're all old stars here. Huh. Where do you think they might come from? That's what I'll show you when we talk about the evolution of these galaxies. In fact, most likely they evolved from these guys, from spirals. Look at this. Look at this. So E0 is most perfect galaxy, is spherical. You can see right through it. It's like no dust, no gas, no new stars, all population 2 old stars, and just stars. That's what it looks like. A little tiny nucleus, little tiny nucleus, like a star. Black holes in the center. Okay, now there's 2 types of ellipticals. Regular ellipticals, mostly they're gigantic, and dwarf ellipticals. So these are called E0. E1 will be a little more like a watermelon. E2, E3, E4 is definitely like a watermelon. E5, E6, E7 is like a cigar, like this. But they don't seem to have anything more eccentric than a cigar. This is it. This is as eccentric as they get, like that. Now, the ellipticals are dwarf. We call them DE0, dwarf elliptical of the 0 kind. DE1, dwarf ellipticals of first kind, and so on. So these are the ellipticals. Spirals start with lenticulars. Lenticulars are spirals that have no spiral arms. Now, why would you call them a spiral if they have no spiral arms? I have no idea, but that's how you classify them. They kind of look like spirals. So they're identical to the spirals, except they don't have spiral arms. They're missing that. We call them S for spiral, 0, S zeros. We call these lenticulars. Then we get to the normal spirals and barred spirals. Remember, we have a bar of dust and gas going through the center too. So regular spirals are classified according to the nucleus. We have a big nucleus and very tight arms. So the tightness of the arms and the size of the bulge or the size of the nucleus. So this guy's got a big nucleus, big bulge, very tightly wound up like a spring. Spiral arms. SA. SB will be, looser, like a medium-sized nucleus. Spiral arms are looser, so smaller bulge, more open arms. And SC, smaller nucleus and really open arms. It turns out that the SC galaxies are some of the biggest galaxies in the universe, actually. Now, we also have barred spirals. They have a bar here. We call them SBA, S for spiral, big B for bar, BAR, bar. So spiral with a bar of the A kind. Large nucleus, spiral arms come from the end of the bars now, right? So they don't come from the nucleus here. They come from the end of the bars. And then we have some with the open arms, smaller nucleus, SBB, and then SBC. So SBA, SBB, and SBC. And this classification, yes?
All right, which ones are considered lenticulars?
Lenticulars are the ones that look like spiral galaxies, but they have no spiral arms.
Thank you.
S zeros.
S zeros.
Yeah, S zeros. And most of the spirals are gigantic, humongous spirals. And you'll be surprised when I show you guys the very first galaxies that were born from the Hubble's deep images. Okay, so next time I'll show you guys a whole bunch of pictures of galaxies and what's going on with the collisions and stuff and how they live their lives and how they evolved and things like that. That'd be the evolution of the spiral galaxies and the evolution of everything else in the universe. Okay, I think we're at the end of the lecture.
So which one are we?
I'm sorry?
Which one's the Milky Way in this?
Oh, very good question. Excellent. I was going to do it next time, but I'll do it now. It's SBB. That's what we are. Remember, we have a bar, spiral arms and everything. So yeah, so we're SBB. Let me show you real quick and go back to the beginning. There you go. You see the bar? Spiral arms coming from the end of the bars. Fairly good sized nucleus. So we're SBB.
That's really cool.
Yes, of course. Of course. Of course. Of course. Let's see. I have another. Okay, yeah. That's Jennifer. All right. All right. Thank you so much for coming in, you guys. I appreciate you guys. You guys have a wonderful day. I will see you.